Welcome to the, I think, fourth session of the Lugano Philosophical Colloquium. Today, I have the pleasure to introduce Karen Crowther. She's actually, I would say, one of the main figures of philosophy working on quantum gravity. She has very important works. She has a book actually published with Springer on a PhD dissertation, I think, based on the PhD dissertation. She worked a lot on the emergence of space-time in quantum gravity, as I would say most of the philosophers working on quantum gravity are doing. But now she is focusing more on like the constraints for a theory of quantum gravity. And I mean, it's my pleasure to introduce Karen also because I really like her work and she's a dear friend. And so yeah, please, Karen, the floor is yours.
Yeah, thanks very much. Thanks. So yeah, as Marta just said, I started off by, with my PhD, looking at this theory of quantum gravity and trying to understand kind of what these different approaches might mean. What could they tell us is going on in the world? What are they saying is the possibilities for this fundamental metaphysics? So if space-time doesn't exist at this fundamental level, how could it emerge? So I was really interested in these kind of metaphysics questions and theory interpretation. And then, I finished the PhD and I got, quite a lot of attention for this emergence, and I still get invited a lot, when you finish the PhD, you get a bit stereotyped in a way. I'm just like, I'm the emergent space-time person. So I was getting a lot of invitations for this. But then I actually, maybe because you spend so much time doing a PhD, I got a bit bored with the emergence questions. And I also started having a bit of a crisis. Like, what am I doing with my life? Because all these theories of quantum gravity, well, we don't know if they're real. It's not like trying to interpret quantum mechanics or thermodynamics, established theories of physics. We don't have an established theory here. We've got these different approaches, and I'm trying to interpret what they could be telling us about the world. But then it really is like, what if it's all just completely wrong? So I moved away from thinking about these kind of metaphysics questions and turned instead to a more epistemological project now, which is kind of asking, well, why are we even looking for this theory in the first place? So that's the question for today. Why do we want a theory of quantum gravity? And it's just been, I've written it up for Cambridge Elements in Philosophy of Physics, and I've emailed the draft. So if you want to read it, you can have a look at this, as well as a shorter paper based on that book. So you'll have both there. Okay, so, it's not clicking. There we go. So, what is this problem of quantum gravity? So we have physicists who've been looking for a new theory of fundamental physics called quantum gravity. And they've been looking for it for a very long time, 100 years, and they haven't found it yet. So instead, I think one of the problems here is that normally when we're looking for a new theory of physics, we're doing it because there's been some conflict with what we've observed in the universe. So normally we're looking for a theory because there's been kind of a discrepancy between what our theories are telling us is the world is like. So something you've observed that's not in accordance with your current theories, or else your current theories have predicted something that you haven't observed. And there's this kind of mismatch between the empirical and the theoretical. And you can think about this in the case of quantum mechanics, where we had experiments that motivated the need for the new theory. Also, even special relativity, there were experiments that kind of helped develop the theory. But it's not so in this case. So we're looking for quantum gravity. There are things that are kind of empirical problems. So problems like dark matter and dark energy, but they're not what's being taken to motivate the need for this new fundamental theory. Rather, I think most of the work, most of the motivation for looking for this new theory are actually philosophical problems. So talk about conceptual problems, philosophical dissatisfaction, also theoretical problems. And when we're kind of in this domain, there's not much of a line between theoretical and conceptual either. So I guess I had a bit of trouble with the slides before because my computer broke. It's like the standard excuse for everything, right? It did actually break. And so we have these two pillars of fundamental physics currently. General relativity, which is describing gravity and the curvature of space-time among massive objects. And then we have quantum field theory, which is describing fundamental particles and fields, the fundamental forces of nature in terms of the standard model of particle physics. So we think of these as like the two pillars of fundamental physics. And the problem is that they're saying kind of very different things about the world, right? I'm not going to go over this. I'm assuming there's some background in physics or, yeah. So I'm familiar with this, but the idea is, you know, typically we can get away with using one or the other picture, but I think there are some places where you kind of can't get away with using one or the other picture. You have to kind of put them together. So, and that would be the theory of quantum gravity. So I'll come back. Where was I? This one. Yeah. So I think we don't have any observed anomalies that are motivating the theory. We don't have a theory. And I think we also don't know what this theory should actually be like. What is it actually supposed to be doing if we can't directly even kind of apply it? So instead, what we've got is these kind of different approaches towards trying to find this theory, different ways of trying to put together GR and QFT, and they're all doing quite different things. They're starting off with different assumptions, they're using different methodologies, and they have different criteria of success, meaning they're kind of aiming for different things. So even when we're talking about quantum gravity as kind of this general label, like what is it that we mean by quantum gravity when it's supposed to refer to kind of any of these potential approaches, I guess? So I'd say it's whatever theory satisfies the principles and constraints that are taken to actually define the theory. That's what I was interested in looking at. So my idea now is to kind of look at the various motivations, so the reasons why we're looking for the theory, and also some of the constraints on the new theory. So constraints meaning that if we're going to accept this new theory, it needs to satisfy certain principles. And then the idea is to look at these and motivations and the constraints, see what kind of principles actually underlie them, and we can philosophically assess these principles in order, one, to kind of better understand what the theory should be like. And we'll also start to kind of question it. Maybe some of these principles aren't well-founded, maybe they have different consequences. So to just, you know, make them explicit and start to kind of understand and philosophically criticize them. And then, so there's two stages, I guess. The first is just kind of laying them out, and the second stage is to actually do the evaluation and see how they're being used in the different approaches, which I haven't done yet. Okay, so I'll start by saying a little bit more about what I mean by motivation constraints. I'll then come to what I see as kind of the primary motivation for quantum gravity. So the one that's kind of driving everything here. And I think there are two ways of satisfying, or two different perspectives on the problem. which is kind of standard perspective and what I'll call the new framework perspective. And I'll finish by saying a little bit about its relation to other motivations for quantum gravity, because there are many different reasons why being cited looking for this theory. So when I talk about motivations, I literally just mean kind of why we're looking for this theory. So I'm going to look at kind of any possible motivations that physicists are citing for saying, yeah, this is a reason to look for the new theory. But also any other ones that maybe aren't being cited, but could be motivations for looking for the theory. So it's a descriptive project, just kind of laying them out. I'm not looking at kind of the most popular ones, just whatever, any of them, really. And here we can distinguish between internal motivations and external motivations. I think internal motivations are when you're looking at our current theories themselves, so GR and quantum field theory, problems within those theories taken as they stand. So the theories themselves on their own terms, separately. So some problems kind of internal to general relativity, which make people think that we need something else to replace it, space-time singularities, cosmological singularities like Big Bang, also black holes. This is cited as a reason for looking for a deeper theory, a reason why GR cannot be fundamental. But also within quantum mechanics, we've got the measurement problem, which I'd say most people don't take as motivating the need for a new theory. Instead, they're trying to solve it by having different interpretations of quantum mechanics. But nevertheless, there are people like Penrose who really think, no, this measurement problem is a problem motivating a new theory, kind of more fundamental than quantum mechanics. So those are the internal motivations. We also have external motivations. So I think external motivations are kind of, external, any external issues from our theories. So kind of things like this desire for coherence or unification, reasons for wanting to bring our theories together, but also any kind of problems or puzzles that arise from our attempts to put these theories together. So in a way, it's a bit like problems of our own making. They're not problems with the theories taken on their own terms as they stand, but problems that we've come up with that motivate us to look for a deeper theory. And I think kind of these are stronger, the external motivations are being stronger than the internal ones in the case of quantum gravity. So those are the motivations, and some motivations can also serve as constraints. So constraints, I mean in a very kind of strong term, criteria of theory acceptance. So any potential theory or approach to quantum gravity, if it doesn't satisfy certain criteria, then it just won't be accepted as a candidate theory for quantum gravity. So I think some of these constraints can come from the motivations, but of course there are also additional constraints that any theory should satisfy, which aren't serving to motivate looking for the theory in the first place. So for instance, we have constraints that come from our current theories in the domains of success. So where we know that our current theories work, the new theory shouldn't kind of violate those. It shouldn't be in conflict with those where we know the current theories work. So think about symmetries there, for instance. Also, there's this need, any new theory is supposed to explain the success of its predecessor theory, the theory that it's replacing. New theory, we know that this old theory is wrong, but it's successful. And from the perspective of the new theory should explain how it was that the theory was successful. And typically how that's done is with this idea of correspondence, showing that you can derive the approximately derives the older theory in its domain of success. So that's a big constraint on quantum gravity. And of course, we also have empirical constraints. And here I think we have different classes of empirical constraints. They do play a role on the new theory, of course. Firstly, we have observations that are not explained by our current theories. So here you could think about dark matter and dark energy, for instance. We also have constraints, those observations that are explained by our current theories, and these ones can be accounted for by, is this actually, no. Where was I? I thought I had a laser on it.
You're the point, it's not the laser, it's point. Yeah.
Hey. Okay, so these ones, the ones that are explained by our current theories, can be taken into account by using this idea of correspondence. It's not very precise pointer. So that second point can help with the empirical constraints that are currently explained by our current theories. But also there's the potential for future discoveries in the field of quantum gravity phenomenology, which is trying to find some observations and empirical tests of the theory. So these ones I've said, they're not directly motivating the theory, but nevertheless, they can serve as constraints. So I think the constraints, especially those ones that are coming from the motivations for looking for the new theory, they can then be used to form part of the definition of the theory. The theory needs to satisfy these constraints, and that is what we're looking for. That's what's defining the new theory. So we have motivations, we have constraints, and then we also have, I think, other desiderata. So kind of nice things that the theory could have. So these are things that are not necessary as constraints. So we would still accept a theory, even if it doesn't have these features, but it would be nice if the theory did have those features. So things like unification, UV completeness, meaning that the theory is able to describe all the highest energy scales or the tiniest length scales, or explanation of particular theoretical problems that come together, and it's cool. Look, we weren't expecting this from the theory, but it's done it. So that's kind of a nice thing that the theory does. So these desiderata, yeah, they might serve as motivations without being constraints. So it might be that we're deliberately looking for these things, or it might be just unexpected bonuses. And in those cases, these desiderata, they can serve as means of non-empirical confirmation. So Richard David talks a lot about this. It's kind of evidence for your theory being successful, reason to accept the theory, or indicators of pursuit worthiness, kind of reasons to think that if we develop this theory, it will be successful in the future. So reasons, or that it's generating nice problems that we should work on. So reasons for pursuing the research program. So yeah, made this diagram for the book. I think we can kind of classify them. Motivations, if they are necessary, then they'll serve as constraints. And then we have some constraints that are not motivational, but nevertheless kind of have to be there. And then we have the ones that kind of are motivational and form part of the definition of the theory. And the motivations that are not necessary, they're kind of forming these desiderata, kind of nice things it would have, but otherwise not necessary. And then these desiderata, as I said, they can be kind of expected, meaning you're kind of using it as a heuristic, and it may be that the theory satisfies it or not, but you're starting off by exploring it. Or they might be unexpected, those kind of nice bonuses that I mentioned. So I think I'll turn now to the primary motivation for quantum gravity. So thinking kind of, what is the minimal characterization of this theory? What is it that all the approaches are doing such that we even classify them as quantum gravity? So I think this is kind of the primary motivation. Basically, it's a search for a new theory of fundamental physics that describes the domains where both general relativity and quantum field theory are thought to be necessary, and which somehow combines or takes into account the lessons of both these theories. And I think this is really, as I said, it's based on this kind of external motivations, desire for a complete, consistent description of the world. So we want a coherent picture of the world rather than having this split picture. Okay, so it's had those already. So the way I framed it is very general, you know, it's not very precise. I haven't made it super precise yet. I think this is something that people can look at. If you want some research projects, you can look into it. But at the very least, we've got three things that need clarification. Firstly, describes. Second, domains. And thirdly, takes into account. So I'll say a little bit more on each of these. Starting with this idea of domains. So where do we expect quantum gravity? So currently, we do have a theory that combines GR and QFT. You can call it low energy quantum gravity. It's basically just GR treated in the framework of quantum field theory. The problem with this is that it's thought to break down at high energy scale. So it breaks down around the Planck scale, and then you can't use it. So the Planck scale, yeah, it's very, very small. I was like writing a popular article about this. I'm like, how do I explain it? So you can look at kind of the scale of the entire observable universe, the diameter of the entire observable universe, and then the Planck scale, and then kind of the geometric mean in between those two is actually kind of the smallest distance that we can see with the naked eye, which is actually the size of the human egg cell or like the strand of hair. So you can think about that. So the size of your strand of hair or your egg cell to the entire observable universe is the same as from the Planck scale to that cell. So that's how small it is. So this approach at combining our theories, it breaks down at that scale, and then we can kind of think, well, what happens here? Maybe it's a symptom of these kind of external inconsistencies. So there might be that this approach is internally inconsistent, but nevertheless, we can still apply it in other domains. But then this kind of indicates that where we need the new theory of like quantum gravity proper will include this Planck scale. So I'm saying UV better, meaning that it has to describe higher energy, shorter length scales than this current approach does. So that's helping to define the domain where we're expecting this new theory to apply. And also, as I mentioned, it's supposed to apply to black holes, the interior of black holes, cosmological singularities, and early universe cosmology, describing the Big Bang, the initial conditions of the universe. So those are the domains. And then the second question is, well, what does it mean for a theory to describe a particular domain? Ideally in physics, it's that the theory has been applied to that domain, given you predictions, and then these predictions haven't been falsified yet, or you've actually tested them. This doesn't work in the case of quantum gravity, so kind of need a kind of a broader understanding of describes here. So something a bit more minimal would just be that the theory gives you formal predictions, which seem physically reasonable, so they're not kind of going off to infinity, things like this, when you've applied it in those domains. So I think this is kind of an interesting thing as well. How do we know that it's actually describing these areas that we think we want it to? Nevertheless, we can also have these kind of empirical constraints that I mentioned, including these correspondence relations that kind of gives you approximately the same predictions as our current theories when applied to the domains where we can test. And then kind of from induction, we can hope and infer that it's also giving correct predictions in these domains where we cannot test. So this is kind of a way to think about. And finally, thinking about what it means that the theory combines GR and QFT. So this second condition, I think, there's different ways of understanding it, but I think two ways you can find here in this quote from Ashtekar. He says, everything in our past experience tells us that the two descriptions of nature we currently use must be approximations, special cases which arise as suitable limits of a single universal theory. That theory must be based on a synthesis of the basic principles of general relativity and quantum mechanics. This would be the quantum theory of gravity we are seeking. So from this, I think we can pull out kind of two kind of necessary features, which mean combines. So firstly, that the new theory is going to recover our current theories in their respective domains. And secondly, that it's combining the principles of both these theories. So when I'm saying combining or synthesis, he says, it doesn't mean that we kind of have to bring in the principles of both and merge them into some new principles. It can be just that the new theory features one or more principles from each of the theories. So one principle from GR and one principle from QM would kind of be enough to have them combined in the new theory. So for instance, we might think in GR, this principle of background independence will be key. And there's a tendency to think from QM, this principle of quantization will be important. So different ways, but there are other options to make it. So I think those are kind of the primary motivation there. And then I think there are two perspectives on how to actually satisfy these conditions. The first one I'll call the new framework perspective. This is where we're recognizing this need to recover both GR and quantum mechanics. And I'm finding this in Ashtekar and Georg. I don't know how to say this, so it's hard, right? But to be clear, this idea of new framework perspective is a label I made up. And in the text by Ashtekar, he is not clear on which framework he's actually taking. He's quite ambiguous. You can read different things there. So I'm just using his quotes as inspiration, not to say that these are his views. But basically, you can think of it like you're understanding GR and QM as distinct bodies of universal rules. And then it's not like you're just going to bring in and quantize GR, the gravitational field, in the same way that you quantize all other fields, because from that perspective, it would be that's the standard perspective. Maybe I should start with the standard perspective. Basically, on this one, you're not using the rules of QM and applying them to GR. You're coming up with a whole new body of rules, is the idea. So you want this new framework, completely new framework. It's not just quantum mechanics applied to GR. So the motivations, I think, for this kind of approach would be, for instance, the measurement problem, where you want a new framework, a whole new theory that will replace quantum mechanics as well as GR. And also kind of, there's some other motivations such as the semi-classical gravity, which is another way of bringing in, quantum mechanics and GR, where you keep gravity classical, but you're coupling it to quantum matter fields. There are problems with this, which might indicate that, again, we need a whole new body of rules. Okay, so that's the new framework perspective. An example of this is kind of post-quantum classical gravity by Oppenheim. So basically, the idea is that here you're modifying both quantum mechanics and GR to get a new theory. But this is not really the standard way of doing it. There's not many people who are pushing this new framework perspective. Rather, most approaches fit in with this one I call the standard perspective. So here, you are treating quantum mechanics as fundamental, and in that case, you don't need to recover it because you're using quantum mechanics. It's not being modified in any kind of radical way. So kind of taking the universality of quantum theory as one of kind of the fundamental principles, and then many people say this, but here's a quote from Lowell and others, saying the physical world at the fundamental level is governed by quantum laws, and the classical picture is only an approximation valid at sufficiently other energies or sufficiently large scales. So, and this one, which Rovelli likes to use a lot, quantum mechanics says that all dynamical fields should be quantized. VR says that space-time is a dynamical field, and therefore we need to quantize space-time. So this is the standard perspective on the problem. Yeah. So this is kind of to see the different views. On the new framework perspective, you need to recover both theories because both get modified and replaced by this new body, a new framework. On the second picture, the standard perspective, we're treating quantum mechanics as fundamental, and in that we don't need to recover it because we're still using it, and treating this universality of quantum theory as fundamental principle. Yeah, hopefully that's clear. So, any questions on this? We'll come back for discussion, I guess. So then there's more specific ways of satisfying this. So Butterfield and Isham, this is a very seminal work in the philosophy of quantum gravity in 2001. They're describing 4 different ways to approach quantum gravity. The first one is to quantize GR. The second one is to have GR emerge as kind of the low energy limit of a quantization of a different classical theory, or as having it as the low energy limit of a quantization of a theory that's not a quantization of classical theory, or the fourth one where you just start out of nowhere with a radically new theory. So on their kind of framework here, or schema, I would say these first 2 options count as a standard perspective. And this last one would be a case of the new framework perspective, but this middle one could be either, kind of depending on whether or not we're treating it in the framework of quantum mechanics or not. So that's how we see the different classifications. And yeah, as I've been emphasizing, the dominant approach by far is that first one, where not only is quantum gravity supposed to be a quantum theory, it's one in which gravity is quantum. So far I've been talking about kind of these 2 pillars, but then there's also another perspective on this, which is bringing in, of course, the third pillar of fundamental physics, which is thermodynamics and statistical mechanics. And this is becoming more and more, I think, recognized thanks to a lot of the discussions about black hole thermodynamics. So this idea that we're kind of using quantum field theory in curved space-time. Hawking shows that black holes radiate and can be treated as thermodynamic objects. So there are some examples of approaches to quantum gravity that do incorporate the thermodynamics aspects. So Jacobson is talking about the Einstein field equations. He shows that they can be derived from proportionality of entropy and black hole horizon area together with the first law. There's also emergent gravity approaches. So thinking of space-time as kind of as thermodynamics or like an effective entity. So on that view, it's like quantizing sound waves, right? You end up with phonons, quanta of sound, rather than kind of the fundamental building blocks or the atoms of space-time. And Panorama and Verlinde, they also argue for gravity emergent in this way through entropy. So there are some approaches along these lines as well. So I haven't really included them in that standard, primary motivation. There's kind of, I guess, the two pillars version of the primary motivation and then a three pillars version of the primary motivation. So finish by saying just a little bit about kind of the other motivations for quantum gravity. So I think they can all be seen as leading to the primary motivation or motivating the primary motivation. So as I mentioned, the measurement problem in QM might be a reason to seek a theory that satisfies the primary motivation. Need for a complete cosmology, so to have a theory that's describing the initial conditions of the universe, the early universe. Will lead you to seek a theory that accords with the primary motivation. The hierarchy problem, so this is a problem in particle physics. This question like, why is gravity so weak compared to the other forces? Maybe this is reason to seek a new theory of quantum gravity that would satisfy this motivation. In GR, if you're concerned about time and you want some kind of becoming rather than just kind of this block picture of time in GR, this might also be a reason to seek a theory in accordance with the primary motivation. Yeah, these arrows, I haven't really thought of how they fit together, but I think some of the, so roughly the arrow should be motivates, right? So I think the primary motivation, it can be, it can motivate a unified theory, but I should have also put an arrow going back because I think the desire for unification can also motivate you to seek this theory of primary motivation. And similarly, unification can also motivate a theory that's a quantization in kind of a minimal sense, because then gravity is brought in under the same framework as the other forces. So yeah, the arrows are motivates indicated. We also have kind of problems or inconsistencies with the semi-classical theories or hybrid theories, which I said are the ones that are including PR and quantum theory, but doing so in such a way that we're kind of treating gravity as classical and every matter as quantum. So on those types of kind of hybrid pictures, they're not really unified. So the problems with them might motivate a unified theory. And they also kind of are linked to this black hole thermodynamics. And singularity resolution, I mentioned in GR, we have these singularity theorems. They're typically viewed as a big problem. Marta can tell you all about this. One kind of motivation or way to get rid of them would be to quantize GR. So that can motivate quantization and also motivate a need for a new theory to replace GR, which satisfies the primary motivation. So I think that is about all I have to say. So in summary, I've said, I think we want to look at quantum gravity, and my idea is to kind of look at the motivation. Why are we seeking this new theory? Kind of better understand what it should be like, and whether we can modify some of these or kind of more critically examine these different motivations. So I've tried to start off by giving the most minimal characterization of quantum gravity in terms of the primary motivation, which is, I said, describes the domains where GR, like quantum field theory, are both supposed to be necessary, and a theory which combines the principles of both. So I think we can then also kind of look more closely at each of these other motivations that I mentioned, and see exactly kind of whether they should serve as constraints as well as motivation, or whether they're non-necessary, and so on. So kind of thinking about the different roles of these principles. And I think kind of many of these other motivations, they're coming already from working within having this primary motivation in mind. So the primary motivation really driven by this desire for consistency and to have this coherent picture of the world. So I think we can then kind of, from this perspective, start to classify and evaluate the different approaches we have to quantum gravity. How well do they fulfill these constraints? And along the way, I think we've come up with this kind of question that has been a bit neglected, I think. Why are we taking quantum mechanics as fundamental? Maybe we should be pushing for a radically new framework that replaces both theories. So yes, that's it. Thank you.